Okay, good morning everyone. For lecture today, I'm going to show you some three key ideas. Three main key ideas. The first one is how you can use the theory that you learned before to design filter size for boost converter. And in that, I'm going to show the process from step 1, step 2 until you can make an Excel form that you can use the formulation to compute all necessary components. The second idea is to show how you can use tool for simulation, for making simulation of your model, especially boost converter, and from that you can observe some key parameter or variables, or especially on the output, the behavior of the output. And then the last idea is to show the process how you can get to building a boost converter. So you're gonna see step by step, but I don't go I don't go in detail. I will just show briefly on those steps. Actually there are many steps in order to have validation of experiment by simulation. Of course, starting from understanding principle of theory that you learn from the lecture, and then you can you know how to estimate component size, okay, and to have the for the second idea that I mentioned about using tool to do simulation, for example Simulink. For now you don't have MATLAB Simulink yet, so I suggest you install it. You can use the trial version. Okay, you can have 1 month to use it, especially student from France. When you are back to France, then you can have you can use in the software in the school. Well, so I'll go briefly. Actually, for the theory, of course, you learn from very detail from each component. You understand those components, especially as the main parameter of each component, because when you build a model in Simulink, you need to use the right parameter. So I'm gonna jump straight to boost converter here. So from the theoretical part, you have the schematics of boost converter like this one. So in this the key that you can have voltage of the output greater than input is to use switching technology, which is MOSFET that can be controlled via the control gate from microcontroller. Okay, and this is the actual components that you're gonna use for boost converter. So you need to note, to recognize each component and some terminal that you're gonna measure to see the behavior or the characteristic of the signal. So let me review the function a little bit. I start from this one, the schematic. So when we control the switch function to be on and off with the period time t, and during the on period we call the duty cycle. We can compute, or we can denote this duration by duty cycle d. Just use d times t, and you can generate the signal from this microcontroller. Then it's gonna make the MOSFET switch on and off in here in this branch. So when it's on, the energy charge in inductor. When it's off, the energy will be released to the load. And this way you can have voltage at the output V2 greater than V1. V1 from the source here, and V2 is at the load. Okay. And so to have to make it easy for you to recognize the schematic, so we built one boost converter, very simple one, using junk component. Actually, you can find this one from desktop computer, and you can easily purchase MOSFET and other components from electronic store. Okay, so I think so far so good. All right. So in this schematic, we don't really mention internal resistor on the schematic or circuit, but actually internal resistor exists inside this wire of inductor. And if you use a battery as the source, it also has internal resistor. So you cannot avoid internal resistor at all. Then next, I'm gonna show the process to estimate component size. So here, so the first step, of course, you start from requirement. So you want to operate one system, so it has requirement, meaning to say the power of the output itself. So power of output has to be known and first, and at the same time you also know the operating voltage, because you design, you choose, you know that the component at the load needs a certain voltage, so you know V2 as well, and from this you can and then you can calculate current. Okay, so there are two ways. The first way is that you already know your system and the load, you already know the power, and you know the operating voltage. Then automatically you can calculate current I2. Or if you design a completely new system that you don't know how much power it consumes, so you choose the operating voltage V2. Okay, so you know V2 first, and then you need to find the currents. How you know that how much current it consumes? So you need to look at all components, each component in the whole system. Okay, you have this block, that block, this block. So and you check on the specification of each one, that how much current it consumes, and then you add up for all of them if they are connected in parallel. If in series, you just use one current, the highest one, something like that. So you know you get the V2 and I2 from requirement. After that, you need to compute the required power source. Okay, source power. So you must consider efficiency, because any system cannot have 100% efficiency. So in this case, most of design based on experience, you choose efficiency from experience or from literature. Or if you are really new to this field, to this system, and you just want to test a rough, demonstrate a rough function or behavior, just pick efficiency. Let's say 85%. You are not very good in designing it yet. You don't have experience. Just choose 80 or 85%. Okay, no need to be very exact, right? So once you choose efficiency, then you can compute current, because of course when you pick up a source like battery or power supply or something, then you already get the input voltage V1. So the remaining parameter that you need to compute for the source is current. So the current equal current time V is power, and the source, the power at the source time efficiency equal to the power of the output. So from this you can, actually you start from here, P2 equal to eta P1, and you have I1 V1 in here, you have I2 V2 in here, then you can get I1 from this term. So after you have all the main four parameters, I1 V1, I2 V2, then you can start one more step. You need to choose the report ratio. It's like how good you want your system to be. So how much the report ratio, the fluctuation of voltage and current you allow to have at the load. So you choose a report ratio RL and RC. For example, 25% or 10%, it's up to you. The smaller you choose, the bigger the size of the components, for example capacitor, inductor. And then you can start calculate some key parameters, for example duty cycle, because duty cycle is the parameter that define the how much you want to boost the voltage of the output. Okay, and then you can calculate capacitance for capacitor of the filter and inductor, also energy storage of these two filter components. Why you need to compute energy as well? Because you are going to choose the component from when you buy those components from commercially available on the shelf, so then it already has the specification. Then you need to compare whether the specification of the component that you bought with what you calculate, okay, whether they can store enough energy or not. All right. Oh, I think I missed one thing. The frequency of the pulse PWM, pulse width modulation, you need to choose as well. And the recommended range is 1 kilohertz to 1 kilohertz to 62 kilohertz. Cannot be more than this and should not lower than this. All right. Okay, so if you look at again, you notice that there are different type of parameters. One type is requirements. Okay, requirements and efficiency, you can just say it together, and then computed parameter, and also selected parameter. Okay, requirement, this one selected by yourself, okay, or choose by yourself, and computed parameter here and here. Okay, right. So from this process and the formulation that we have in the theory, then you can build an Excel to compute, because so you start from parameter that you choose, for example efficiency 85%, voltage at the output and voltage at the input, you from requirement, and current from the output first, and then you compute current for the input. Okay, and you know the output voltage and current at the output, then you can compute the load resistance. Okay, for ripple, you choose it. You choose ripple ratio for capacitor and for inductor, and then choose frequency. For example, here's 7,800 kilohertz, so 7.8 kilohertz. So why this number? Yeah, actually in microcontroller there are certain of frequency available. So we cannot choose whatever we want. We need to know the function of microcontroller as well. As you can see here, this is for Arduino Uno or Arduino Nano. And then duty cycle. Okay, duty cycle is computed from the schematic in order to have voltage at the output boost, okay, from the voltage of the input. So yeah, actually based on this formulation. Oops, not here. Boost. This one is back. Yeah, this one. Okay, so you can compute the duty cycle from this formulation. You know V1 and V2. And then you can compute capacitance and inductance, right? And this the computed value are a mean value, which means you can choose any capacitor or inductor that has larger capacitance and inductance than this value. Okay. So once you have these parameters and you choose the actual component and you get the actual parameters from their specification, then you can build a simulation model in Simulink Simscape. So again, I suggest you install MATLAB trial version. We can use it for 1 month. Okay. So next time we will work on this simulation. So today I'm going to show that from the simulation we can have a result. After then we compare the result with the actual device. Yeah, I will show some steps to prepare materials and tool and documentation in order to build, just for those who may be interested to build it, to experience from the very bottom up. Yeah, so you prepare all materials and tools, and then you can just see the list here, and also some components, yeah, some specific components that need to be used with boost converter and buck converter. Then I'm going to show the actual component, the actual one there already. Yeah, so I'm going to show the result of boost converter first. This one is not boost converter, I guess this one. Yeah. So from MATLAB Simulink, the result is to be like this. The waveform of the voltage at the output at the load. Okay, at the load V2. So the average value can be slightly different from the simulation and experiment, but at least we can see that the waveform, the ripple, okay, the ripple waveform between simulation and experiment to be almost same, almost exactly the same. Okay. So this demonstration is for you to extend how you design your system, for example, to be bigger, or you want to add on more functionality, or you want to have feedback control. So you learn from the simulation that okay, we have the tool and we configure parameter in this way, and then we can get the result of simulation almost same as experiment. Then you can extend the simulation model, and then for many systems you only iteratively work on simulation, and you trust that simulation reflects the actual. You don't need to do the iteration on the actual device, so it's gonna consume a lot of time, right? Yeah. Okay, so the main idea here is to know the process, the steps, and good practice. Okay, good practice is to work on most of the time work on simulation, because you can save lots of time when you start the experiments. All right, so I'm back to this schematic. This one is buck, so this one is boost. So you're gonna check with the actual device just to see some important signal. For example, the signal sent from microcontroller to the FAT, and you also observe the output signal from the FAT here. So here. Okay, so first you observe this signal, this one with respect to ground. So I just draw only one, because all the signal you compare to ground. So first check this one. You see this one, number one, and then number two you check this one output from the FAT. Okay, and the last one. You're gonna see output from the resistor here, number three. Yeah, of course, if you want to know the input, the signal of the input, you can check this, just call it step 0. Okay. Okay. So you're gonna measure all this to see the waveform in the oscilloscope. Okay. All right, any questions so far on this part? So, by the way, anyone have ever seen all these components before? I mean, like inductor, capacitor, microcontroller. Have you seen and experienced some measurement on these? Most of you, yes. Maybe not. From the look on your face, maybe not. All right.